Hello everyone. In this video, we will be going through questions 11 to 15 of the SMO Senior 2020. In question 11, we are given a right-angled triangle ABC. And ABC has a 30-degree angle, which makes our life already seem pretty good. We have got a 30, 60, 90 triangle, and we know one of the side lengths. We are also told that CP is the angle bisector of angle ACB. So our 60-degree angle is sliced into two 30-degree angles again. So far, so good. And finally, Q is a point on BC such that AQ is perpendicular to CP. So we are asked to find the length of PQ. Now, with all these 30-degree angles everywhere, we should immediately know that we can find most of the lengths that we want to find. And that's because of your ratios in such a triangle being 1 is to square root 3 is to 2 for a 30, 60, 90 triangle. In fact, if we look at CP here, it kind of looks like it is a line of symmetry between A and Q. So let's try to use that to relate all the stuff on the lengths of AB, AC and BC to PQ. Now first up, I should call this point something like X. Then triangle CAX is congruent to triangle CQX. That's because we have a common length, two 30-degree angles and the right angles. So this means that X is the midpoint of AQ. And that being the case, it means that now AXP is also going to be congruent to QXP. In other words, this is quite an elaborate way of saying that CP is the perpendicular bisector of AQ. So A is the reflection of Q over CP, and that means that specifically AP equals to PQ. So we have accomplished our first task, which is to shift PQ somewhere onto the triangle. Now after that, we're just going to use these ratios to find AP. So AB is 48 cm. That means that AC is in the ratio 1 is to root 3. So AC would be 1 over root 3 times 48 cm. And now if we look at triangle ACP, that's also in the ratio 1 is to square root 3 is to 2. So that means that AP is 1 over root 3 times AC, which becomes 1/3 of 48. And that is 16 centimeters. So pretty straightforward, because A, the figure is very symmetric, and B, all the right-angled triangles in this figure are 30, 60, 90. So when you have all these special angles, what we immediately know is that one angle brings all the other angles, which makes the question much easier as a result. Next up is question 12. This is a circle geometry question. O is the center, and we are given a couple of angles. AEB is 70 degrees, and AOB is 62 degrees. So we're asked to find the angle OCD. To be honest, we have quite a lot of options as to how to proceed down here. Amidst all of this, your main priority should be just to find a way to get to angle OCD, because we really can find almost any angle in this circle given enough time. So let's zoom in to angle OCD. The only thing special about angle OCD is that it is part of the triangle OCD, which is obviously going to be isosceles since O is the center of the circle. So that means that to find OCD in this isosceles triangle, here's my plan. To find angle OCD, I'm going to get it from angle COD. Now in turn, angle COD is an angle at the center. So we can use this to relate to an angle on the circumference. And it would make sense that we do it for something like angle CAD. So let's draw that in as well. And to find angle CAD, we can see that angle AEB is an exterior angle. So most of these pieces are already joined together. We are now going to do it forwards based on this idea. First step, angle AOB would be 2 times of angle ACB. So that means that angle ACB is half of 62, which is 31 degrees. Now that means that angle CAD is equal to angle AEB minus angle ACB. So subtracting it off, 70 minus 31 is 39 degrees. Now based on our plan, we can backtrack from here to OCD. So angle COD is twice of CAD, which is 78 degrees. And finally, that means that angle OCD is 180 degrees minus 78 over 2, which is 51 degrees. So this is something that we can do for geometry if there are seemingly many reasonable options. We try to work a bit from the back so that we know what sort of intermediate objectives we could have. Instead of finding every single angle in this diagram, we look for which angle would help me to find angle OCD. And that way we can get a more direct path as opposed to meandering all around the diagram and finding 12 unnecessary angles along the way. In question 13, we have yet another trigonometry problem. We're asked to find 4 cosine 43 degrees over sine 73 degrees minus 12 sine 43 degrees over square root 3 sine 253 degrees. To be honest, trigonometry questions comes in all shapes and sizes. It comes with lots and lots of different combinations. So we are always looking for anything interesting whenever it is just a bunch of numerical values. So it's not an equation to solve. It is just a bunch of specific looking angles. So we should figure out what is so important about these specific angles. Now at the top, we have 43 degrees repeated a couple of times. At the bottom, we have got 73 degrees and 253 degrees. Now we realize that 253 degrees is just 73 plus 180 degrees. And so that means that sine 253 degrees is actually negative of sine 73 degrees. Hence, both of these fractions actually have sine 73 degrees in their denominator. So we can combine them together and treat it as a single fraction, which already looks a little better than before. So let me just change sine 253 degrees to negative sine 73 degrees. And I'm going to take 12 divided by square root 3, which is 4 square root 3, and therefore leave sine 73 degrees as the denominator. Now we are left with 4 cosine 43 degrees plus 4 root 3 sine 43 degrees over sine 73 degrees. At the top, we can see that both of the angles are once again 43 degrees. So because both of them are 43 degrees, we can combine them together using the R formula. If we combine them together using the R formula, R would be the square root of 4 squared plus 4 root 3 squared. This is 16, this is 48, and so the overall value is 8. Now for those of you who didn't learn it as the R formula, R just really represents the range, so the maximum and minimum value. And so we can therefore write this as 8 times sine of 43 degrees plus the tangent inverse of 4 over 4 root 3. And 4 over 4 root 3 is 1 over square root 3. The tangent inverse of 1 over square root 3 is just 30 degrees. So we're happy with this because it gives us sine 73 degrees back again. And therefore our answer reduces just to 8. Most of the time when you are given an expression to evaluate with a bunch of specific angles, those specific angles are not chosen at random. They are all related to each other in some nice way. The 43 degrees are repeated at the top, while at the bottom the two angles differ by 180 degrees. And furthermore, between 43 and 73 degrees, the difference is 30 degrees. There is also a special angle. So take note of this whenever we are solving such questions. We are supposed to do it without a calculator. So you kind of anticipate nice coincidences along the way, and you should take advantage of those nice coincidences to guide your solution. Next up is question 14. If x squared over 5 plus y squared over 7 equals to 1, find the largest possible value of x plus y squared. Okay, so this question, to be fair, needs a little bit of additional knowledge perhaps. You would like to use the Cauchy-Schwarz inequality. Now the Cauchy-Schwarz inequality is something that we can apply in many instances, and I'm just going to state the result first. So for any real numbers, a1 to an and b1 to bn, if we calculate the sum of squares of a1 to an and multiply it to the sum of squares of b1 to bn, this is greater than or equals to a1 b1 plus a2 b2 until an bn squared. And equality holds if a1 over b1 equals to a2 over b2 and so on until an over bn are all equal to some constant. So I should say if and only if, meaning that this is the only time when both sides of this inequality will be equal. As a quick side note, this is actually a simple result when we use vectors. You can think of this as having a vector A which has n dimensions, the vector B having n dimensions, and then this statement really just says that the length of A squared times the length of B squared is greater than or equals to A dot B squared, which we know is true since A dot B is actually the length of A times the length of B times cosine of the angle between them. Now, if you're not familiar with vectors, no issue, this inequality can be just used directly as well. For me, one way that I like to think about it is that A1 squared and B1 squared, you take the geometric mean of these two to get A1, B1. You then take the A2 squared from here and B2 squared from here, and you get the geometric mean A2, B2, and so on. Now let's apply this to this question. So it gives us one initial example of how the Cauchy-Schwarz inequality can be used. So x squared over 5 plus y squared over 7, this is 1. Now I'm going to multiply this by 5 plus 7. Now here, we can use the Cauchy-Schwarz inequality to state that this is greater than or equals to just x plus y squared. Now you may wonder, how exactly did we get from here to here using Cauchy-Schwarz? And the answer is that A1 would be x over root 5, A2 would be y over root 7, B1 would be root 5, and B2 would be root 7. Now this is not a very convenient way to think about it, which is why I mentioned that in effect, we are taking the geometric mean of x squared over 5 and 5. So you multiply them and square root, it gives you x. You multiply these two and you square root, it gives you 1. And that's what effectively happens over here. Now since this is 1 and this is 12, that means the maximum value is just 12. Technically speaking, this is not quite complete. We should also say that x over root 5 is to root 5 is equal to y over root 7 is to root 7 in the equality case. So it happens when a1 over b1 equals to a2 over b2, which is when x over 5 equals to y over 7. In other words, x is to y is 5 is to 7. Now I'll leave you to see the actual value where this works out. I think it is going to be 5 over root 12 and 7 over root 12, but you can work out the details on your own. Finally, question 15 asks us to find the coefficients of x to the 6 in the expansion of 1 plus x plus 2x squared to the power of 7. If you have seen the binomial theorem before, then you know that this is not a binomial, this is a trinomial. And since this is a trinomial, we don't quite have the ability to apply the binomial theorem and immediately get an answer. Now it is possible to use the binomial theorem by splitting it up into two sections, 1 plus x and 2x squared. However, that is a little bit slow if we were to split it up like that, and I would like to also explain a bit about how we can understand the binomial theorem and generalize it to multiple terms. We see that the power here is 7, and there are 3 terms, 1, x, and 2x squared. So let's think about what combinations of these would give us x to the power of 6. Firstly, we could have 3 of 2x squared multiplied together, and that already has a degree 6. So we cannot have any more of x, means that the rest of them would be 1. Now we could also have 2 of 2x squared, which leaves us with x to the power of 4, and we can take 2 more of x, and the other 3 would be 1. We can take 1 of the 2x squared, 4 of x, and 2 of 1. Or we could use none of the 2x squared, 6 of x, and the last one is 1 itself. Now these would be 4 different combinations of terms being multiplied together to generate x to the power of 6. So let's count the total coefficient. Now firstly, if we have 4, 0, 3, there are 7 choose 4 ways to pick 4 ones, and then 3 choose 0. The term here is going to have 2x squared cubed, so there will be 2 cubed resulting from 3 of these 2x squared. Next, you can have 7 choose 3 times 4 choose 2, and you have 2 squared from the one below. In the third case, you have 7 choose 2 times 5 choose 4 times 2. And finally, you have 7 choose 1 times 6 choose 6. Now each of these are relatively small, so it is not very difficult to calculate them. And you have got a fair number of small terms like 3 choose 0, 7 choose 1, 6 choose 6, 5 choose 4, which will all simplify out. So I will leave you to do the computation, and that gives us 1337 as the final answer. Alright, so this brings us to the end of this video. In the next video, we'll be looking through questions 16 through 20.